Okay, today we will talk about firewall and intrusion detection systems, since we just finished discussing the network security. Firewall and intrusion detection systems, they are closely related to network security. Ooh, sorry about that. So, firewall and intrusion detection systems, they are closely related to network security. But they're not only limited to network security. So a firewall, traditionally, a firewall is a component that restricts access between a protected network and the internet. So inside the firewall, it's kind of like a gate. So inside a firewall, we have our own network, which is a trusted network. Outside of the network, we have the internet, which is untrusted. So the firewall basically interconnects networks with different trust and imposes restrictions on network services. So only authorized traffic is allowed. So firewall can also audit and control access. It can implement alarms for abnormal behaviors. So when we do that, we actually becomes an intrusion detection system, or in this case, a network-based intrusion detection systems. So firewall provides perimeter defense. So, but there are other kind of firewall as well, not necessarily just network-based firewall. We'll also have a host-based firewall. All of your systems, no matter Windows, Linux, Mac you are using, that system itself has built-in firewall. So this is a screenshot of a very old Windows system. This probably is Windows 8 or something, and you can say, it has a firewall. So there is a P2P software BitTorrent tries to connect to the network, and the Windows firewall can block it. Also, even your home router, if you go back home, connect to your home router, then you can say your home router probably also have a firewall. You can set different rules there to specify what traffic is allowed, what is not allowed in your home network. So how does firewall works? It basically analyzes the inbound and outgoing packets against some rules and decide to block or allow the packet based on those rules. So firewall provides those kind of mechanisms to do that. Then on top of that, we have different rules, and those rules, we also call them the security policies. And those policies specify allowable packets in terms of some logical expressions on the packet field. For example, it can allow transport layer data, for example, based on the IP address, the source address, destination address, based on the protocol, based on the TCP headers, the flags, or based on the ICMP message types. So the firewall will read each packet header and decide if we'll allow that packet to get through or just discard that message. It obviously applies to both incoming and outgoing packets. For example, this is another one, Windows firewall. This is a built-in Windows firewall, and there could be many policies or many different rules. And usually, we follow the first match rule. We go through all the rules one by one, and the default we can set those, all the packets should be denied. Then we go to the first rule to say if this incoming package is governed by the first rule. If the first rule says this should be allowed, then we allow it. If the first rule didn't say anything, we go to the second rule. Eventually, we may not find any rule talking about this specific package. In this case, we just deny. We discuss discard that packet. For example, we have a rule: no incoming port. The port number 53, except from a known trusted server. We know that the DNS use port number 53. At the server side, the DNS use the port number 53. So when you make a DNS request and you get the DNS reply, then the source port in that IP packet, your DNS, not IP packet, your TCP packet, that DNS message will have the source port number 53. Then for your home computer or your home network, you can set a policy like that. If there is a package coming from the source port number is 53, then I will only accept that packet if it has a trusted IP address. For example, 348, right? Only that I will accept that, because only that I will trust this is a legit DNS reply. Of course, I mean, the IP address can be spoofed, as we discussed in the last 2 weeks. That is solved by DNSSEC or some other protocols. So the protocol could look like this. Also, let's say we want to allow inbound emails using the simple mail transfer or transport protocol, SMTP, which use the port number 25. But we only allow that to go to our gateway machine. We do not allow that to go to all the machines in our network. Also, we assume that there is a malicious website called malsite, and anything from that website, from their IP, our firewall will just block that. Then we will have 2 rules here. The first rule is, as long as the source IP is malsite, no matter what other fields has, we just delete this packet. We just discard this packet. For packages that are not from this site, then we will say if the destination is our gateway server and the port number is 25. Only if that, we will allow that. If it's not our gateway server, even if it has a port number 25, we will also deny that packet. So suppose that we want to implement the policy, any inside host, trusted host, can send mail, but nothing else. Cannot send anything else to the outside. Then the policy may look like this. We only allow the IP packets sending TCP packets sending to the port number 25, because 25 is for the SMTP protocol. So if you're trying to launch your browser, visit the website, it will use port number 80, then the firewall will deny that. So this is a simple way to implement this, and this is only based on the destination port number. And actually, we do not have any way to control the destination port number. So an attacker can access any internal machines and port by originating from port 25 on an outside machine, which means that on that outside server, on the port number 25, usually we will run the SMTP server, the mail server, right? But the attacker, they can run any other applications on that port. Do not need to be the SMTP. So this cannot really defeat those kind of attacks. So to make the rule a little bit more, the policy a little more robust, we can do something like this. We have 2 we have two rules. The first rule says for any of our machines, it will be our host. Their outgoing TCP packets, the destination port has to be port 25. If it's that, then we allow the packets. Then for any other incoming packets, if they are from port number 25, then we have to say their ACK flag in the TCP header is set, which means it cannot be a SYN flag, which means the attacker from the outside, they cannot use the port number 25 to initiate a collection to us. It has to be a collection initiated by our hosts, not the outside server. So this is how we can defeat some kind of attacks from the outside, which pretend to be from the port number 25. So firewall blocks packets from outside of the network with a source address inside the network. This prevents an outside attacker spoofing the address of an internal machine, because the firewall can say that the message on a particular port, their source IP should always be outside IP. It doesn't make sense that the source IP is an internal IP. So we can easily block that. Of course, if the attacker, they are trying to spoof another outside source IP, then our firewall will not be able to detect that's a fake IP. Also, the firewall can block packets from inside of the network that tries to spoof an IP address outside the network. But the same thing, if the attacker, an inside attacker, just try to spoof an inside IP address, the firewall cannot really detect this is a fake packet. To detect that, we will need the IP layer protocols we discussed before, like the IPsec, to add authentication to the IP header. Also, another limitation of a firewall is it doesn't work if the inside host is compromised and it tries to attack or spoof other hosts in our network. So, for example, we have a big enterprise, and the firewall's network firewalls were only configured at the gateways. Then whatever happens inside cannot be detected by the gateway firewalls. But of course, a large enterprise can be divided into many smaller zones, many smaller groups, and in each group, they can have their own firewall. Even like I said, like all of you, your laptop, it is somehow in its own zone, and there are already firewall on top of that as well. Here's another example. We have a web server, and we want to apply the policy like packets from or to the website are allowed only if an outside host initiates the collection. So the policy can be something like, first of all, this is a web server, so the port number will be 80. Then the IP address would be the web server's IP address. This is a simplified policy, and this policy cannot really achieve this goal. Like package from a website are allowed only if an outside initiates a collection. So this policy basically allow all the TCP IP packets between any outside host and our server and it doesn't really care who initiate the collection. So using the similar approach we talked just now, we can actually use add more fields to the policy. So the policy can look like this. The first rule is the source IP and the source port can be anything, okay? Because whoever launch a browser to connect to our website, they may use any port number. Also, any port number in their own machine. Then when their package goes through some kind of network translator, network address translator, the port number may change as well. So we cannot really limit what the source port is. Also, we don't limit what the source IP is because we know anyone in the internet to talk with us. Then the destination will be our server and port 80. However, we require that it is either a SYN packet or a ACK packet. Then for outgoing packet, the source has to be our web server. The destination can be anyone, but however, it must be a ACK packet. So it cannot be a SYN packet itself. So which means if the website try to initiate this collection, then the firewall will block that. So how is this useful? Assume that you host your website on a third-party hosting service like GoDaddy.com or Google App, some platform like that. And your website is somehow compromised. Some attacker compromised your website and use your website as a springboard to attack other systems. So if you have rules like this, then you will say that the source IP will be maybe a VirtualBox, virtual machine, it's IP, but the source IP do not necessarily use 80 because in this case, you initiate the collection and 80 is reserved for receiving the incoming web requests. Then those rules will block that. So even if your website is compromised, it will not be the machine you're running on the website is compromised. It will not be able to use as a springboard to attack other systems. So also for firewalls, there are two different categories. One is called stateless firewalls. Stateless firewalls, they do not remember the TCP collection states or other information about the packets. So they don't remember the history of packets. They don't have the concept of a flow, right? They only look at each packet. So every time you get a packet, look at the packet as an independent one. Do not think about previously there was another packet and they are related. Then there are also stateful firewalls that can remember the history. Let's say this example, we have a client, we have a server. The client has IP address this, and the server has this IP address. Then the client send a UDP package with this source port number 3264, source IP address, that's the correct IP address, and the destination port number, then also a destination IP address. You can say those are correct information. Send this packet to the server, and the firewall in the middle try to remember that information. The firewall remembers, I just got a message, UDP message, like this. Then later, the server replies with another UDP packet with the correct port number, IP address. Then then the firewall will compare those two packets and say, oh, because of the first packet, I know the reply is also a legit one. However, if we look at the third packet, in this case, the server tries to send a UDP packet to the same IP address, however, to a new port number. So this port number never contact the server before. Then, so here we can say the port number is 2049. So this port number never try to contact the server before. So the policy here could be the server should never initiate any kind of communication if the client never didn't initiate that. Then the firewall can remember that, and this do not match our history, then deny this. Also, different hosts, they may basically different computers. They may have different firewall needs. So some of the computers, they want to be accessed by anyone. For example, a web server. Some of the hosts should only be accessed by people with authority. So the solution to this is something called the DMZ, Demilitarized Zone Networks. And all our modern network firewalls, they support something like this. Today, you go home, you connect to your wireless router, you go to the admin page of your wireless router, and you can look for if they have a DMZ setting. Usually, they have. So in international affairs, a DMZ is an area which agreement between nations there are agreements there. Basically, it's a buffer, and usually that's the region that you forbid any military installations or activities, right? So here the concept is similar, but also different. So in the computer network, the DMZ also provides this kind of a buffer zone to separate the internal network and also from the outside network. So let's say we have the outside network, which is the internet, where there could be all kinds of malicious packets going on. Then we have the DMZ network, which is also under some kind of firewall policy. But the policy will not be that strict. We will allow more packets to go to the DMZ network. However, behind the DMZ network, we have our own real internal network. And from there, we will apply another set of policies, rules. So for the malicious packets from the internet, it will be harder to get into the real internal network. Maybe easier to get to the DMZ network. So if you go to your router setting, your modem setting, you will find something like this. You will be able to set a DMZ zone, which can include several IP addresses. Then those IP addresses will have a virtual DMZ zone. Then they will have a little bit different firewall policy there. So let's say one example. Let's assume your home router, you set a very strict rules there to basically protect all the devices in your home. Could be iPad, your phones, everything. However, you also have a PlayStation, which you want to play games. But because the rules you are setting at your firewall is very strict, you are not be able to do a lot of things in your PlayStation. You cannot join games. You cannot speak using headphone or whatever. Basically, the firewall will block those kind of communications, right? Then how do you make this work? Is you set up the DMZ, and in that DMZ, you use different firewall policies. You get the IP address of your PlayStation. Usually you sign it as a static IP address. Or you can also do a dynamic one anyway. Then you sign that IP address in your DMZ ROM. Then from there, you have different policy. Okay, so that is how you can basically at least to have two different set of firewall policies just using one router. So all the routers right now support something like this. So like I said, firewall is kind of like the first line of defense. It's like a gate. But obviously it doesn't protect you from all kinds of security problems. So it should not give you the false sense of security. Nothing should give you that. You should always live in fear, actually. You should always know there are danger everywhere, especially when it comes to cybersecurity. Firewalls, they do not look at all the fields. The examples we showed before, they are looking at the IP headers, the TCP headers. But things are also changing in recent years with the concept called software-defined network, SDN. I don't know how many of you heard about SDN before. No one heard about SDN? Some of you heard about SDN. So SDN is an idea came from Stanford several years ago, and most major network providers, they embraced this idea. So basically, this is one of the efforts in the movement of software-defined blah, 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 right? So now you can see a lot of software-defined cars, software-defined radio, software-defined network. The idea is to move a lot of configurations of things that used to be hard-coded or baked in hardware, move that to software. Now we can change them. So SDN is basically changing the behavior of those networking devices like routers and switches. So they do not just do what the first in the first network security course I told you guys, switches does this, routers does this, and that was baked in the hardware. So now the routers, the switches, or now we just call them all of them switches, they will do much more than that. And what they do is determined by software on top of that device. So they do not only look at the IP headers. So the switches, technically, they should only look at the MAC address IP headers, right? Routers only look at the IP headers. But now they can look at the IP headers. They can look at the TCP headers. They can even look at the application headers or even application payload. So when they look at the application payload, they are not just doing routing anymore. They are doing deep package inspection as well. They want to say if the payload has some malicious content, something like that. So now the switches can do something like that. So what I have on slide here is a little bit obsolete. Or in other words, firewall doesn't have to be a hardware anymore. It can be implemented as an application on top of switches. Now those switches are programmable. Also, firewalls, you can generate a lot of logs. Then how to analyze those logs actually is also a very hot research area because all those networking devices, they generate a ton of data every minute. How to automatically analyze them, quickly analyze them to find suspicious activities is very important. So if you use Linux, Linux provides a stateful firewall itself. It's called the IP tables. At the user land, it's called IP tables. It's an interface for the Linux LED filter kernel module. and it supports all kinds of rules on this. On Linux devices, you can use those kind of commands, IP tables, blah, blah, blah. You can add rules to those tables. Of course, because it's under the hood, this is a kernel module. That's why you need to use to do this as a root user. By the way, did anyone here know that sudo was actually developed at UB originally? Wow, some of you actually know that. Yeah, I only knew this last week when some of our faculty members shared the news about that. Interesting. Okay, so IP table, let's say. So Linux level IP table, you can use it as a host-based network firewall. Also, you can host-based firewall. You can also use it as a network firewall. Let's say we have a computer here. This computer act as the gateway for two other networks, network 2, network 3, and also it connects to the internet. So this computer, this Linux box, can just act like a networking device and using IP tables to specify the rules. Let's say it can say any package forward to me to blah 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 IP address based on the IP tables, or for a router, it's called routing tables. Then I will decide to forward to which port, which hardware network interface. So we talk a little bit about the IP table architecture. You don't have to remember all the details. Just want to give you a little bit a sense how this is designed. So there are 5 chains in IP tables, one for each point in the kernel's processing path. If a packet comes in, it will first to a system, then it will first go to the pre-route chain, then input chain. It also could go to the forward chain and post-route chain. Then it goes out the physical interface. So all of this is part of the Linux kernel. So the chain determines when a packet is examined. An incoming packet arrives at the hardware interface and will be processed only by the rules on the pre-routing and input chain. Then the outgoing packet will be processed using the output and the post-routing chain. So if the host acts as a router, it will forward some packets. So they will go through the pre-routing, forward, and post-routing chain. So if we go back to the example we had before, you can see there are 3 commands. And we are adding rules to those chains. So this is adding a rule to the post-routing chain. This one is adding to the forward chain. So this is basically the command to say how many packets we have processed at each chain. You can say in this example, we already accepted this many packets, this number of data, and we didn't forward anything. So probably in this case, this computer is not acting as a router. Okay, it's just a regular edge device. Then the output part, then the policy allow us to send this many of that data out. So those are the information. So besides the chains, there are also 4 tables. A rules table determines what targets are valid for that rule. as well as to which built-in chain the rules can be added. There are some targets like or actions like accept, drop, and then there are filter tables, network address translation, net tables, mango tables, and raw tables to do many other different things. So this is like a full packet path. When the packet coming in to the computer from the network, it will first go to the pre-route raw table, then go to pre-route mango table, then pre-route network address translation table. Then it maybe go to the forward mango table and filter table, something like that. So that's how the kernel, the network filter module in the Linux kernel was implemented. Here are some examples how to use this, but in this class, I didn't really design experiment for this, so we are going to skip this part. If you are interested in something like this, we do have a network security course in the department. Maybe we're going to offer one network security course starting from next semester, actually. So we're talking about something like this in details. So going back to the previous example, we have a gateway. The gateway has 3 network interfaces. Assume they are all Ethernet, then we just call it Ethernet 0, Ethernet 1, and Ethernet 2. Then the gateway will just forward the packets between those networks. Then this is how we are going to set up this IP tables. We will set the IPv4 IP forward as true. Then we will add in this table, let's say this is at both the post routing. Then we will say the out interface will be Ethernet 0, right? So here it's Ethernet 0. So basically tell us if we get any message to forward, we should forward to Ethernet 0. Also, if we get any, well, this is also for this is for Ethernet 1, we need to append the forward table. So basically for any message we get at Ethernet 1, we will just forward that to Ethernet 0, right? So there's several commands we can configure our Linux box as a router, basically. Okay, we will skip this part. So next we will talk about intrusion detection systems. They are also another very important network security device, not only network security, and actually the concept of intrusion detection is so broad. Any attack can be considered as an intrusion attempt. And for any attack, we want to detect that, we want to prevent that, and after detection, before detection, maybe the best thing is we can prevent that from happening. But if that failed, at least we should be able to detect that. Then after detect, we want to respond. So intrusion detection, we also have host-based intrusion detection. We have network-based and also hybrid. So a lot of system security guys, what they're doing is also intrusion detection. Then, since there are intrusion, then there are also attackers or intruders. Then some of intruders, they are just hackers. They break into computers for fun, not necessarily for profit. Then there are criminal organizations, organize the crimes to attack high-value targets. And also, they may obscure the trace. So after, so that's why when some cybercrime happens, also there is a forensics team, network forensics or computer forensics team, try to analyze what happened before. Also, there are insiders, employees who misuse their privilege with or without a malicious party. Okay, so the recent is that DoD? The recent information leakage from DoD, that is also insider attack, right? So that's why some agencies are very interested in how can we stop this kind of insider or detect insider attacks. Let's say, okay. So the intrusion detection systems, they basically monitors and analyze system events. And when they discover something malicious, something suspicious, they just raise an alarm. So there could be host-based intrusion detection systems, there has been a lot of work, for example, to monitor the applications, the user-end applications. At the kernel level, they will monitor what this application system calls, how often they make system calls, the parameters they use to make system calls, whether the pattern of that match a pre-trained benign model. If it doesn't, it means this application is trying to do something malicious, right? That's a host level. Then the network level, then we can monitor all the packets in the network, try to correlate those packets. Let's say if there is just one ping packet, there's probably nothing suspicious. Someone is pinging me, that's okay. But if there are 1 million ping, which is the SNMP packets, ICMP packets, coming in 1 minute, the 1 million. And if you correlate that, you'll say probably this is a denial of service, distributed denial of service attack targeting at my computer. So all those intrusion detection systems, they monitor the events, and a lot of them try to use machine learning or deep learning methods to classify if this is a malicious or benign activity. So deep learning based approaches has been really popular in recent years. Before that, was just rule-based or signature-based. So actually, the signature-based or rule-based approach, we used to call them misuse detection. They can detect low-end intrusion attempts. For example, we have a rule. If in the last minute there were more than 10,000 ping packets sent to me, I say raise alarm. That's an attack, right? That's a very specific rule. Because it's a very specific rule, it may not be correct. It may not be robust. It's possible that someday just 10,000 people decide to ping you at the same time, not necessarily an attack, right? Then, or other approaches, most approaches we use right now, not only in academia, but also in industry. For the last 5 years, I would say a lot of solutions are based on deep learning, machine learning. We call those approaches anomaly detection. So anomaly detection basically train the system based on some benign data and try to model those benign behaviors. Then at runtime, just to try to monitor real data and to say if the real data match the pre-trained model. So it's hard to explain those in very concrete rules, right? So give you a machine learning model, technically, still, eventually it maps to some rules. So I don't know how many of you took machine learning class before, right? How many of you use something called a support vector machine, SVM? So technically, when you use SVM, the decision you are making is still based on the rules. Just that rule is not at the original dimension. It has a hyper dimension. There is still surfaces in the hyper dimension. If you cross the surface, the decision would be true or false. On the other side, it will be a different answer. But it cannot be, usually it cannot be mapped to very concrete human understandable rules. I would say that would be the major difference from the traditional misuse detection to this anomaly-based detection, machine learning or deep learning based. So intrusion detection systems, like all other machine learning, deep learning systems, are not perfect. There are errors because those problems, they are not decidable problems, basically. They are undecidable problems. Then there will be false positives, there will be false negatives. False positive in this case means there was no attack, but we misclassified them as attack. Then false negative in this case is it was actually attack, but our system didn't detect that. For different scenarios, sometimes false negatives are more serious than false positive. Let's say your website, you set up a website, maybe you get 1 million web requests a day. And in that 1 million web requests, there is only one malicious. But that malicious one can bring your website down. They find a software vulnerability of your website. That one malicious request bring you down. So if your IDS doesn't do anything, then the false negative rate is actually still very, very low, right? 1 out of a million. That's the false negative rate. You only reported one wrong. 1 out of a million. But just that 1 out of a million false positive rate will bring down your server. Okay. So as defender, false positive rate usually result in higher loss than false positive rate. So if you have a false positive, let's say your system, even though there are 1 million requests to your website, then your IDS flagged 10,000 of them. Or maybe that's too much. Maybe flagged 100 of them as malicious ones. The real malicious one is also there. So the false positive rate here is also very high, right? 100 out of a million, which is 1 out of 10,000, basically, right? So it's still a relatively high false positive rate. But because of the false positive rate, you find all 100 potentially malicious ones, and you stopped all of them. Then you stopped attack. Your system will still be available. Let's say IDS. So actually, a lot of research I do myself, I would call those are host-based intrusion detection. We mainly one of the projects we are doing right now is at those very low-end microcontrollers. We get a trace of all the instructions executed. Then we analyze all the trace and to say if there is any control flow hijacking attack, like the one you did in the software security course. In the software security, in those you did 4 challenges, I remember. So in those 4 challenges, there are either return address on the stack or some code pointers. And your job was to overwrite those so it can call the print flag function, right? So that attack actually violates a property or a rule we call control flow integrity. Basically, when a program executes, all the control flow transfer should match the control flow we allowed for that application. So if there is a function call, then the return should return to where the function called it, right? You cannot return to another function like print flag, right? If you return to another function, that's a control flow violation. And we do a lot of research on how to detect those kind of violations, how to stop those kind of violations. So that's why I call what I do. A lot of them are actually host-based intrusion detection. Of course, this can be done at many different levels. You can do this at the usernet level, software level. You can do this at file system level. You can do this at a socket level, kernel level, many different layers. Network intrusion detection systems. I actually also work on that a little bit. So we call them NIDS, network-based intrusion detection systems. So they monitor the traffic in the network. So usually they passively receive the copy of traffic. And it's a little bit different from firewall. Usually firewall was sitting between your hosts and the internet. And the firewall directly decides if your packets can go through. Usually network intrusion detection systems, traditionally network intrusion detection systems, they do not sit between the hosts and the internet. They sit, they are also basically a host in the network as well. So they do not directly decide if we should stop this collection or not. But like I said, now things are blurry with things like SDN. All the switches, they can implement intrusion detection. They can also implement a firewall. So the boundary is actually very blurry now. Traditionally, we talk where we position them actually matters. We can, let's say we have an external firewall, then we have many different local networks, workstation network, service network. So in this kind of network architecture, if we put the network intrusion detection system or getting traffics from this place, obviously we have a bigger picture, a complete picture of the traffic. The whole enterprise traffic we were able to see. But also there is another challenge is in the last decade, a lot of network traffic becomes encrypted. So previously it was not. Okay, 10 years ago, we're not using TLS or HTTPS for everything. Now all the website you are visiting, you are using HTTPS. If you visit a website, just use HTTP. Your browser will tell you, hey, you should not trust this website. 10 years ago, not like that. So because of this, everything is encrypted. The intrusion detection systems right now, they cannot really see the payload of the data, the packets. They only see the unencrypted part, the IP headers, the TCP headers, maybe application headers. But after that, everything is encrypted. Even if now you send a malware through the network, if you use HTTPS, the malware is encrypted. After encryption, the network intrusion detection system cannot really tell. After encryption, everything is just random bytes, right? That's what our encryption does from our early classes. We learned this semester. So the encryption is to increase the entropy of data. So after encryption, organized data look like unorganized, look like random bytes, right? So a lot of network intrusion detection systems right now, what they do is just looking at those headers, the IP headers, TCP headers, but they're looking at the headers of many, many packets, not just one, and try to relate all the packets. Cannot look at the payload anymore. So used to, what we do is to look at the payload, and we used to call that a deep packet inspection. Basically, you look at the payload, you look at the application layer data. For example, you can kind of like your antivirus systems. So your antivirus system, we can say that's kind of like a host-based intrusion detection system, right? So your antivirus system will look for some unique strings. Those strings could be wildcards, including wildcards. Those unique strings represent some kind of instruction sequences. And those instruction sequences could be malicious. Like in those 4 software challenges you did, when you send out those strings to those 4 challenges, the program was hacked. So those strings we call the exploits. Then some of the exploits can be very complicated. Not only just what you did there, like 20 bytes. It could be much longer. So when they are much longer, there is a higher chance that we can find some unique strings, which is also long. The unique string could be 20 bytes, 30 bytes, or even longer. And whenever we see that unique string in any of our files, in any of our network traffic, then we say, oh, this unique string is part of a bigger exploit or a bigger malware, malicious software, right? Then we can detect those attacks. However, if they are encrypted in the network, then network, at least the network side, you will not be able to find those. But even if they may be encrypted in the network, after they get to your file system, they may be decrypted, right? Then even if in your file system, they may be encrypted, when you want to use it, you still have to decrypt that. So in the memory, it's still plain text. That's why there is also a research area, memory-based intrusion detection system. So they do not analyze your local file system, like antivirus. They analyze your memory at runtime to see if in memory there will be something malicious decrypted. You can even push that even further, okay? Even in memory, those malicious things could be encrypted. They were only decrypted in the CPU cache. Actually, someone did something like that. It's called cache malware. So the malware will only be decrypted in the cache, and the cache is not synchronized with the memory. We actually have some project to detect those kind of cache malware. So you can always push this further. To do research, you can always push this further. So the early network intrusion detection systems, the very first one is called the BRO. I believe that's the very first one. It was developed by a professor at UC Berkeley. He is still a professor there. He made a lot of contributions to security and also network. He developed BRO. Then there was an open source. I remember Snort was an open source project. It was very, very popular 10 to 15 years ago, but recently I don't believe they are that popular anymore because of the encryption. The network based intrusion detection is a different area from before because you cannot do deep package inspection basically. Let's say some of this is a little bit obsolete. Some of this is actually about how to attack the old intrusion detection systems, for example, BRO. So Bro has its own hash table implementation and use very simple exclusive OR to do that implementation, and it's very easy to find the collisions. Because of that, there were some attacks on the intrusion detection system itself. Basically, attackers were able to do a DOS attack on Bro. So Bro were just run very, very slow there. And also all kinds of invasion techniques have been developed to bypass network intrusion detection systems, especially now when they are based on deep learning and machine learning. In deep learning machine learning, how many of you heard something like adversarial machine learning or adversarial deep learning? This happens everywhere. For example, if it's a computer vision task, let's say autonomous car, will use cameras to look at the signs on the road. Maybe it's a stop sign, but if just you put some stickers on the stop sign, then the stop sign will not be recognized as a stop sign. Instead, it will be recognized as something else, right? So that is something called adversarial machine learning. If NIDS is based on deep learning, we will have many of the same problems. If now you go to top security conferences, if you go to network section or machine learning section, you will see a large body of research is on this kind of topics, how to attack those deep learning based intrusion detection systems. Okay, let's say that's basically all I have for firewall and intrusion detection systems. Any questions? Okay, so I see you next week. I believe we have only 2 more classes.